In our last explainer, we talked about fused multiply-add operations. Well, today, we're diving into something a little more sinister, a silent killer that lurks in the world of physics simulations and the clever engineering that can stop it cold. Welcome back to the explainer. We're looking at a really fundamental problem in game development and physics engines today. How do you build stable, predictable systems when the very math you're using, floating point math, is built on shaky ground? So let's start, not with code, but with pure chaos. Physics simulations, they live and die by math, but standard floating point numbers can be like shifting soil under your feet. And the biggest threat? It's a value called NaN, which stands for not a number. It can pop up from something as simple as dividing 0 by 0. And as you can see here, that one tiny error at frame 0 can spread like a virus, unseen for dozens of frames, corrupting everything it touches until, boom, a catastrophic data explosion. So you have to ask, right? Why is this even allowed to happen? Well, the answer is buried deep inside the rules of the programming language itself. Okay, let's get into the weeds a bit. The language we're talking about, Rust, has a super strict system for defining what it means for two things to be equal. And that's where the trouble starts. You've got total equality, or eq, for things like integers, where, 5 is always equal to 5. Simple. But then you have partial equality, or PartialEq, and floats get stuck here because of one bizarre rule from the math standards. NaN is never, ever equal to itself. That's a huge problem. And the consequences of that rule? They're massive. Because floats break that fundamental rule of self-equality, Rust basically says, I can't trust you. They don't get the official EQ seal of approval, and that means you can't use them in really important data structures, like a hash map. If you try to sort a list of numbers and there's a NaN in there, your program might just crash. The whole foundation just crumbles. So if your most basic building block is flawed, what do? Just accept the risk? Well, the Titan engine's answer is a hard no. You don't accept it. You forge a new foundation. And here's how they do it. Instead of using those raw, chaotic floats, the Titan engine wraps them in a custom container. Think of it like this. You're taking a volatile, unpredictable chemical, that's your raw F32, and you're putting it inside this perfectly engineered, rigid container called F32. This new container forces the float to behave, manually giving it the stability and predictability that it was missing. But here's the crucial part. This wrapper isn't just a simple box. It's a whole security system with multiple layers of defense. Let's break down the mechanisms that make it so powerful. Titan's first line of defense is all about failing fast. The strategy is simple. Catch the troublemaker before it can even get inside. Every single time a new F32 value is created, there's an immediate security check. If that value is a NaN, the program panics right then and there, at the source of the error. It doesn't wait 100 frames to let it cause an explosion, it stops it at the door. Okay, next problem. How do you sort a list of numbers if one of them is, by definition, unsortable? A standard comparison just won't work. The solution is to stop playing by the float's rules and enforce your own order. And the way this is done is pretty ingenious. Instead of trying to compare the value of NaN, the system looks at its raw data, its bit pattern. It then forces all those chaotic NaN patterns into a predictable quarantine slot whenever you sort the numbers. This guarantees the list is stable and orderly every single time. It literally takes chaos and maps it into order. All right, let's talk about another sneaky logic bug. I call this one the illusion of equality. In physics code, checking if two floating point numbers are perfectly equal is almost always a mistake, because floating point math is really just an approximation. Now, a common workaround is to check if two numbers are close enough, within some tiny fixed tolerance. But that's a flawed approach because it doesn't work at every scale. As you can see here, that tiny tolerance might be fine for small numbers like friction coefficients. But when you're dealing with massive world coordinates, the actual gap between two consecutive numbers can be bigger than your tolerance. The check becomes meaningless. So the elegant solution is something called context-aware equality. It's like using an elastic ruler that stretches to fit the problem. It uses a relative tolerance that scales up or down with the size of the numbers you're comparing. This creates a pass zone that's always proportional, making sure your equality checks are meaningful whether you're working with tiny numbers or gigantic ones. Now, the final defense isn't actually about math at all. It's about meaning. See, just using a raw number and F32 for everything, velocity, distance, mass, that's a recipe for disaster. It's a problem called primitive obsession. If all your numbers look the same, how can you stop yourself from, say, adding a distance to a mass? You can't. Titan solves this by encoding physical meaning directly into the code itself. For example, instead of just a number, you have assigned distance. The type itself tells you what it is. A negative value means two objects are penetrating, a positive value means they're separated. It's not just a number anymore, it's a physical concept. And because of that, the compiler can become your own personal safety inspector. Since signed distance and velocity are now totally different things, the compiler can enforce real-world logic. Trying to add them together is like trying to connect a water pipe to an electrical socket. It just doesn't make sense, and the compiler will stop you, catching the bug before your program even runs.
So what do you get when you put all these different layers of defense together? You get a complete system for predictable, stable physics.
You get a complete architectural solution, the stability stack. And it's not just one clever trick. It's a multi-layered defense built on a philosophy of safety. You start with the solid bedrock of Rust's type system. You add the structural integrity of that F32 wrapper. You build on it with the logic of relative tolerance, and you protect the whole thing with the guardrails of semantic types.
And that really brings us to the final takeaway here. True stability in a physics engine isn't about finding better math. It's about engineering better, stricter definitions for the math you already have. It's about building safety in from the ground up. And when you see a solution this comprehensive, it really makes you wonder, what other silent killers are lurking in the tools we use every single day?
In the next video, we'll explore SIMD, single instruction multiple data, to execute 4 mathematical operations in a single CPU cycle, while leveraging Rust's zero-cost abstractions to eliminate function call overhead.